Hey everyone, this is John Bolton. I am a research scientist at NASA Goddard Space Flight Center in Greenbelt, Maryland. And today I'm going to be discussing satellite-based remote sensing of soil moisture and particularly how that can complement and leverage in situ-based observation of soil moisture that we will be discussing today during the listening sessions. So first I'd like to point out that this figure here, this is the Soil Moisture Active Passive mission, or SMAP. This is NASA's latest and greatest achievement focused on satellite-based observations of soil moisture. This was launched in 2015. I'll go into this in a little bit more detail in a second. So NASA actually has quite a large number of Earth-observing satellites in our Earth fleet, as shown here. We have over 18 different satellites that are focused on different components of the water, energy, and carbon cycles. So traditionally we use radiation-based remote sensing technologies to sense different components of the Earth system. So we see here highlighted on this cartoon of the electromagnetic spectrum, we have soil moisture, snow, ice, rainfall, and vegetation. And the region identified as microwaves, this is the region of the electromagnetic spectrum that is sensitive to soil moisture. And in the next figure, I'll show you how that is done. So in soil moisture remote sensing, there's two main approaches for doing this. You have a passive approach and an active approach. Passive approach you can think of as your eyes capturing ambient light, so you can see. Active is similar to a radar gun, so it emits radiation and measures the backscatter or return. So the passive instrument, in fact, it's a microwave radiometer, is measuring the thermal emission from the land surface, and this is measured in brightness temperature. The soil moisture, in fact, is the dominant effect on that received signal in the absence of significant vegetation. On the other hand, the active component, or backscatter, or radar, is you have the ability of having a finer spatial resolution, and it's also sensitive to soil moisture. However, it's influenced more by vegetation and surface roughness. So the goal here is to try to combine these two technologies optimally, so you can leverage the capabilities of both. Now, the value of remote sensing-based approaches is realized mostly in the fact that you have the capability of having a global perspective combined with frequent revisit times. Now, these satellites are flying at several hundred kilometers altitude, and they're going quite fast. So you have the potential for frequent revisit times, and you have a regional perspective of soil moisture. Now, what you can do with this, it provides an improved understanding of the hydrologic cycle. You can link the processes of the terrestrial water, energy, and carbon cycles, many different applications. But the key here is to have a long-term consistent data record at the highest possible temporal and spatial resolution so that you can strategically merge these with in-situ observation networks. Now, satellite-based remote sensing is not going to replace in situ, and in situ is not going to replace satellite remote sensing. You have limitations with remote sensing-based approaches. You're limited by your penetration or sensing depth, as well as your revisit time is the highest is probably daily revisit time. Yet you have this spatial resolution and regional perspective combined with a global view of soil moisture, and this provides a lot of value when you're applying these. It's interesting to look at the evolution of satellite-based soil moisture remote sensing. Here on the left we see the NISSAR satellites were first launched before 1980. And as technology has advanced, mostly our ability to capture longer microwave wavelengths, so as the fidelity and reliability of the remote sensing-based soil moisture products. Most notably, the NASA Soil Moisture Active Passive mission was launched in June 2015. So as I just mentioned, NASA has a long legacy of microwave radar and radiometer instrument and algorithm design. On the top right figure here, you see a truck-mounted instrument. So these were done as a test bed for future satellite-based sensors. And the next figure down, this is sort of a demonstration of a strategic blending of agronomic information and satellite data and models. So taking these satellite-based observations merging them with in situ observations. So this can be done for calibrating and validating current and even planned satellite products, for increasing the fidelity of the in situ network as well as the satellite-based products. And this leads me to value-added products. So the key here is trying to strategically apply these, merge these with a land surface model or a crop growth model or a soil moisture model, so that you can improve and constrain those models from frequent satellite observations. And from that, you're able to have more informed information, such as the Dynamic Agriculture and Productivity Index, or DAPI. That's a partnership with the National Agricultural Statistical Service and the Foreign Agricultural Service, as well as USDA's Crop Condition and Soil Moisture Analytics, or crop CASMA product. Now let's take a look at what SMAP is seeing. So the objective of the SMAP mission was to provide high resolution and frequent revisit global mappings of soil moisture and landscape freeze-thaw state. The mission target for accuracy was 4% soil moisture and a sensing depth of 0 to 5 centimeters. Now the repeat time of the SMAP sensor is 3 days, so you have a 3-day global coverage capability. And what this animation here is showing is precipitation memory. It's simply just the NASA GPM, or Global Precipitation Mission, observations of precip overlaid with the soil moisture active passive anomalies. And it's pretty cool, and it really captures this idea of precipitation memory. So NASA is also partnering with the Indian Space Agency for an exciting mission planned for launch in 2023. This is the NISSAR soil moisture mission. And what's exciting about this, it will have a much higher resolution of 200 meters, but it will have a more infrequent global coverage of every 12 days. That said, we're very excited for this next horizon of satellite-based remote sensing. Now, as I mentioned before, the value of ground-based measurements is the high accuracy that you have. However, they suffer from sparse and limited coverage. Now, the key here is to combine these with a satellite-based observations. You can do this through combining with a land surface model through data assimilation. In fact, that's what we are showing right here. This is the NASA USDA Global Soil Moisture Data Assimilation System. And by doing this, you're able to constrain this, in this case, it's a 2-layer soil moisture model. So you have a value-added product that is also providing global coverage, and it leverages both in situ observations and satellite-based observations. Now, because the SMAP scatterometer stopped working in 2015, folks have been trying to figure out ways of combining different observations to meet that targeted higher spatial resolution that was aimed for with the SMAP mission concept. So what we see here is a demonstration of a finer spatial resolution product produced by Fang, Lakshmi, and others at the University of Virginia and USDA. And what they've done here is they've leveraged this concept of thermal inertia between the daily surface temperature changes and the averaged soil moisture over different vegetation conditions. And the way they did this was that they looked at these relationships over a long historical record using the North American and the global land data assimilation system, GLDAS and NLDAS, surface temperature and soil moisture, as well as observations from satellite, like the Advanced Very High Resolution Radiometer, AVHRR, as well as the MODIS, the Moderate Resolution Imaging Spectroradiometer. And what they were able to do here is produce essentially a MODIS and SMAP-based higher resolution product that is leveraging the surface temperature observations. And here we see comparisons with the coarser SMAP-based 9-kilometer product with the downscaled 1 kilometer and even 400 meter resolution soil moisture products. So this is being produced over CONUS as well as globally. Here's an example of a value-added product that is applying a spatial disaggregation algorithm. Here, this is the thermal hydraulic disaggregation of soil moisture, or TSIM approach, was used to provide 1 kilometer based spatial resolution observations. And what's neat about this is that it's provided in an interface that also provides agrometeorological conditions. And so this allows the partners at the National Agricultural Statistical Service to have quick and easy access to near real-time soil moisture observations as well as crop conditions and soil conditions. So it's very helpful for assessing current and future crop productivity. And it's called Crop Chasma, and there's a link. You should check it out. It's pretty cool. So I hope this provided some context of satellite-based remote sensing and how it's related to and tied and depends really on in situ gauge observations of soil moisture. So there's many interesting applications of soil moisture that are coming about these days, whether it's constraining hydrologic weather models or informing agricultural monitoring or improving flood or drought forecasting. Right here, this is a pretty cool example of assessing fire risk through satellite-based observations. And it's pretty simple and very straightforward. On the top left, you see the time series of observed fire counts from satellite. And on the bottom, you see just a time series of lag correlation of soil moisture anomaly. Pretty straightforward, but also a wonderful demonstration of the value of soil moisture. So that's it for me. Thank you very much for your attention, and I look forward to these listening sessions.